In this video, we are going to continue talking about electrophilic aromatic substitution reactions on aromatic rings. But in this video and in the next few, we'll be talking about what happens when we have some kind of substituent on our aromatic ring. There are different effects based on what type of substituent it is. So we have this table here that summarizes it. So we can have what are called the electron donating groups, and those are the ones here in blue on the left side of this, and those are going to be activating and they're going to be ortho para-directing, and so we'll talk more about what that means here in a minute and how to determine that. Then we can also have deactivating that are meta-directing. Then the halogens kind of have their own thing going on. We'll talk about that in a couple videos from right now. This video, we're pretty much going to be focusing on what's in blue on this table right here. So we're looking at activating ortho para-directing groups. So just as a reminder for what we're talking about here, we're talking about the electrophilic aromatic substitution. We take an aromatic ring like this benzene right here. Again, in this video and the next few, we'll be putting on other substituents, but the reaction is essentially the same. We have all these sp2 hybridized orbitals. We have an electrophile. We're going to trade out this hydrogen for the electrophile. And so we end up with the electrophile on here and the hydrogen leaves. So we're just substituting one of the hydrogens for the electrophile. And so the aromatic rings have resonance. That's one of the things that sort of defines them. And so we have what are called the electron donating groups, which usually have some kind of lone pair on them that can then get brought down into the ring like that. We can also have electron withdrawing groups, which can sort of bring the electrons up out of the ring. And so that can be something like this or something like this right here. And then, like I said, the halogens kind of have their own thing going on. We'll talk more about that in a future video. And so this is what the resonance structures look like for each of these. So for the electron donating groups here and the electron withdrawing groups here. And so what you'll notice is that with the electron donating group, we end up with a lone pair and a negative charge moving about inside the ring. If we have an electron withdrawing group, we end up with positive charges moving about the ring. And so we can see that here with these electron density maps. We see that with the electron donating group, such as on a phenol, that this red right here is a lot brighter. There's a lot more of it. That's telling us that there is more of the electron density in the ring. Whereas if we have something like this benzaldehyde, which is an electron withdrawing group, we can see that there is less of the red and orange color in the ring when compared to the benzene right here, which has this amount of electron density. And so, like I said, these electron donating groups are what are known as activators. So these are going to activate the reaction. They're going to make it more likely to happen. Activators increase the rate at which the electrophilic aromatic substitution occurs, and this is done by using electron donating groups, or EDG. This is either through inductive effects or resonance. The three that we're going to be looking at today are these. If we have an alkyl group, that's done inductively. If it's an alkoxyl or an amine group, those are resonance. And activators like these are also ortho and para directors. So they speed up reactions ortho and para to the group. So remember, ortho is when it's right adjacent to the group, such as on this one or this one here. Meta is when it's just one further away right here, and para is when it's exactly opposite of the group there. And so what we're going to see is we're going to end up with more of the ortho and more of the para products than less of the meta products. First, we'll look at these alkyl groups. So these are just hydrocarbon groups. So something like toluene, which is something that is just a benzene ring with a single methyl group on it, reacts about 25 times faster than benzene under the same conditions. So we say that toluene is activated toward electrophilic aromatic substitution, and that the methyl group is an activating group. Nitration of toluene gives a mixture of products, primarily those resulting from substitution at the ortho and para positions. Because of this preference, we say that the methyl group of toluene is an ortho para director. So we see that we get 60% of ortho and 36% of the para, where we only get 4% of the meta in this case. But this is a little bit deceiving because there are 2 ortho positions and only 1 para position. So each ortho position is actually only getting 30%, where the para is getting 36%. And so the para is actually going to be even more activated, while the ortho tends to be slightly less activated. But because there are two of them, then we end up with more of the ortho in this case. And this is because we see with benzene, when we are first doing the electrophilic aromatic substitution, we add the electrophile onto it, and then we end up with these resonance structures. And on benzene, these are all just secondary carbons that positive charge ends up on right there. But if we do ortho, or if we do para, then one of these resonance structures is actually tertiary, and so that makes it favorable, whereas the other two are still secondary. But if we try doing this with meta, then we are still doing only secondary carbons right here. So by having this alkyl group on the aromatic ring, we can make one of the carbocations in the resonance structures actually be more favorable, because it's going to have the tertiary carbon within it rather than just secondary carbons. And that's why the alkyl group actually makes it para and ortho directing. And we can see that here. If we look at the energy diagram, we see that benzene is higher than the meta, but also the ortho and para. But we see that the transition state of the ortho and para is even more stabilized than the meta. And so we're increasing the rate towards all three positions, but the ortho and para is increased a lot more. And that's why it's going to direct it towards the ortho and para positions. So like I said, alkyl groups are ortho para directing, and they increase the rate of the reaction through inductive stabilization. So we end up with something like this, where we have the ortho and the para being more favored here. What we notice on this one, the numbers are slightly different. That's because we have an ethyl group on here rather than a methyl. And so what we notice is that the general trend here is that as the substituent gets larger, as the alkyl group gets larger, the amount of para product is increasing and the amount of ortho product is decreasing. That's because we have this steric hindrance where trying to add the electrophile, say on this carbon or this carbon, is going to be hindered by this large bulky group right here. And so it's going to actually put it more on the para carbon right there. So as the group gets more bulky, you end up with more of the para substitutions rather than the ortho substitutions. Then if we look at the alkoxyl group here, so something like anisole, which is just a benzene ring with this methoxy group on it right here, we see that this again is going to be ortho and para directing, but this is actually going to go even faster. So it's actually about 10,000 times faster than benzene and about 400 times faster than the toluene. That's because here the stabilization is done through resonance rather than just inductive effects. Resonance in general tends to be a stronger stabilizing force than just the inductive effects. So in this case, we are going to end up with that carbocation on the carbon bound to the oxygen, and then we can have the resonance from the oxygen stabilize that carbocation. So that looks kind of like this right here, where again we can have the ortho where we end up with this stabilized carbocation right here, or the para where we also end up with that stabilized carbocation right there, where with the meta we still have just all secondary carbocations right there. So one thing that I like to think about, and this isn't actually how it's done, but it can be used for bookkeeping on here, is remember when we have the resonance structures, we end up with the lone pair on the ortho, the para, or the ortho right here. And so we can kind of think about it like this. If we end up with these resonance structures, we can have this one come and grab onto the electrophile, we can have this come and grab the electrophile, or we can have this come and grab the electrophile. Again, that's not how the reaction is actually occurring, but if you are just trying to do a bookkeeping and wondering where the electrophile will end up, you can kind of think about it this way, where with the different resonance structures, we end up with a lone pair, either ortho or para, to our electron donating group. But this right here is actually the reason why it's going to be ortho and para directing. That's because we are stabilizing a carbocation right here, or right here, through that resonance. So like I said, the methoxy group is actually going to be even more activating than just the alkyl group, and it's actually so activating that you can just put it into water with bromine in it, and it's actually going to just react. It doesn't even need to have the catalyst in this case. And you will actually end up, if you have enough of the bromine, with the tribromide version of it, because it's just so highly activated when we have that ether group on it. The other one we're going to look at are the amine amine groups. So this one also has that lone pair. It's going to be very fast. Again, if we put this in water without any catalyst and we have enough bromine, it's just going to end up with the tribromide version of it right there. And again, this is because of the same reason we saw with the ether group. We have that lone pair that can come down and actually stabilize the carbocation on that carbon right there for the ortho and the para attack, where the meta would once again only have the carbocation on those secondary carbons, and so it is less stabilized. And so this is kind of the summary here for these activating ortho para directors. We see that the strongest one would be the phenoxide right here, because this has the negative charge on it. So when we end up stabilizing that carbocation, we have a full negative charge right next to it in order to stabilize it. Then we can have the amine group here, then we have the phenol group there, then the phenyl group right there, then we can have the analyde, and then of course we have the alkyl group right there, which is the weakest of the activating ortho para directors. But as we saw with the percents, it's still going to be quite highly ortho para directing. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.